Hey everybody, and welcome back to Algebra 2 online. So the plan for today is to talk about inverse functions, and like I said last time, the reason we needed to do this was the reason we needed to talk about composition last time was so we could talk about inverse functions. And basically an inverse function, if I kind of use this picture over here, the idea is like you can have something go into a function like this pyramid thing and it pops out a sphere. Then if you put a sphere into an inverse function, and we'll talk about this notation, then it's going to pop out that same pyramid diamond thing again. This is a very important thing in the world. Like if you have something that's in like Fahrenheit, let's say, there is a conversion, equation that takes you to Celsius, but we should be able to go backwards from Celsius to Fahrenheit. Or if we were in Celsius, right, we can go to Fahrenheit, and then likewise we can go back to Celsius. So basically, it's something that kind of creates this loop that you see here. Like if you take an x, send it through the function, you get f of x, right? And then if you take f of x and you send it through the inverse, you should go back to where you start. And that's where the composition part comes, because it's like a function used as the input for another function, all right? And so these two are actually inverse functions, and we'll talk about today how to find them. But if I compose them, and it doesn't matter which way I compose them, something important is going to happen that I want you to see. So let's say this is f is green, g is blue. Let's do just like f of g of x. So this is f composed with g of x. So what this is, right? We have like 3 times something plus 9 is f, and I'm going to stick g inside of that. So 1/3 x minus 3 inside of it. And you can see here, if you distribute the 3, right, 3 times a third is 1, and then 3 times negative 3 is negative 9. And then we still had like that plus 9 from the f originally, right? So we can cancel these things, and we can just get x, right? So we started, I'll do it like in white, we started with x, and we ended in x. And that's exactly what this picture is supposed to show you. Start in x, end in x, right? This is like a test that we can do to see if functions are inverses. If we compose them, they better always take you back to where you started. Like if you had even done f of g of 2, right, you should go right back to 2. Basically, g of 2 is going to do like, what is that, 2/3 minus 3, whatever that is. Then if you do f of that number, 2/3 minus 3, I promise you it's 2. Because if you start in 2 and you go through a function, then it's inverse, you go right back to where you start. That's why composition is important, because it's the tool we use to figure out if two things are truly inverses. Okay, quick but really important word on notation. So a lot of times students struggle with this notation. F with the little negative 1 there of x is not equal to this. And I know I just wrote equals, but I'm going to do that. These are not the same thing, and students always want to think they're the same thing. This notation with the little negative 1 here, this is not the function. The function is f of x, right? When I do a little negative 1 there, that's just a naming mechanism, just like g is a name for a function and f is a name. F with a little negative 1 there is a naming mechanism. It is not an operation on a function. This is an operation on a function, right? This is what we call an inverse, okay? Specifically it's the inverse of f. So if you see the little negative 1 on just the letter, inverse of f, or inverse of whatever the letter is, right? This is the reciprocal, and we've seen that with like division problems and things like that. That's the reciprocal of f. It's a very different thing. This is just purely 1 over f of x, right? That's what a reciprocal is. You flip it around. Like you can, for example, do the inverse of f and then take the reciprocal of that, and that would literally just be 1 over the inverse, so you can see, if you can blend them like that, they'd have to be two different things, right? So make sure that you're careful about that. I will be doing things where I have in the same problem this, and I have this. And you have to know the difference. Math is very precise, and you have to be really precise with the way you write math and read math and all that sort of stuff. So, big difference, and I know it's frustrating that they look so similar, but where they are is what's important. This is on the letter, so it's just a naming mechanism, and name is the inverse of f. This is an actual operation on a function, okay? So, important. Try not to forget that. All right, so I want to move towards talking about like how we even get an inverse. But in order to do that, I want to know when we should get an inverse. And that comes back to this idea of being one-to-one or not one-to-one. So we did this way back towards the beginning of the year. Something that is not one-to-one just literally means you have something in your input, or some things, I should say, in your input that go to like one thing. Like here I have two things, 4 and 11, that both go to 5. So this is an example of a function that is actually 2-to-1. Two things go to one thing. 1-to-1 things are really, really nice. You can have like all three of these things, and they all just go to one unique thing, right? 2 goes to 9, 4 to 6, 11 to 5. That is a 1-to-1 function. It's a very nice thing in math. And turns out that in terms of inverse functions, in order to figure out if we're going to even have one, it's tied to this one-to-one versus not one-to-one part, okay? So this thing over here, this line, diagonal lines like that are always going to be one-to-one. They're really nice things in math. Quadratics, on the other hand, are not as nice. This is a 2-to-1 function, right? Like you can kind of see here, let's take whatever, like -1 kind of pops out there, or here. So in this graph, it's kind of looking like -1 and 2. They both map to maybe, I don't know what that is, -3.5-ish, something kind of like that. So the point is that quadratics are 2-to-1. There's lots of times, like there's two roots, right, that both map to 0. The vertex is the only spot where it's 1-to-1, but when we analyze a function, even though here there's a 1-to-1 spot, the 2-to-1 spot kind of takes precedence. This overpowers that one spot where it's 1-to-1, and you always describe a function based on its highest relationships, like highest in order, right? So 2-to-1. So in math, this is what we really, really like and works really nice. This is not so nice. And turns out that there's actually such a thing as a horizontal line test, which can test basically if a function is going to even have what we call a well-defined inverse. So I'm going to start, and I'm just going to write down what the test says. All right, so this is what the test says. So if you can draw a horizontal line over the function somewhere, which hits more than one spot, then f of x does not have a well-defined inverse. Okay. So, diagonal lines, they're going to be fine. Horizontal lines would not be. They're actually like the worst for this test, right? Just like vertical lines were the worst for vertical line test. So this thing is fine for horizontal line test, but let me clear this up a little bit. But this thing, right, I can draw a horizontal line there, and I hit 1, 2 spots. So this thing fails the horizontal line test. And that means that like this is true for any quadratic, they're not going to have what we call well-defined inverses. So what is that? If you think about a quadratic, like x squared equals 9, right? We know that x can be two things here, plus and minus 3. The idea is like, you got -3, 3, let's call that 9, right? And we know both of those two numbers square and give you the height there of 9. But for like a quadratic, square root function, which is the inverse, right? Well, this is the whole point. It's not quite the inverse. If you do the square root of 9, it is always going to equal 3. Square root of 9 does not equal negative 3. And there's no way to even get negative 3 out of it, okay? The square root function looks like this. And if you go and pop in 9, it's going to map back to 3 here, right? But there really should be another part to the graph. There should be this part down here. And this is the part that we're not seeing. And that's where we would get negative 3. Like if that was here, then you could map back over here and get negative 3. But all of that stuff down here in white is not there, because if it was there, then this thing wouldn't even be a function, right? You'd be failing the vertical line test. So it turns out that there's a lot of things in math where if you kind of flip it on its side, right, you can think horizontal line flip into vertical, then you're going to get something that would be failing the vertical line test and not even be a function. So literally what we've done in math, and this is just kind of a weird power that, we've developed a lot of this, and we've made it work for our purposes here and there. What we've done to make it work is we've literally deleted a chunk of this graph. It should be there, but it's not. And if you go graph square root of x on Desmos or in your calculator or whatever, you just get this. And this is what it means to not have a well-defined inverse. The inverse function is missing a whole chunk. Okay, we'll talk about that a lot more, but that's a really important thing with inverse functions and functional analysis in Algebra 2. So subtle, but really, really important. The square root function does not perfectly unpack this. You will never get the negative stuff out of the square root. It's only defined from there on, okay? Not down here. You're not going to be able to get that. All right. So I want to talk about how we're going to even find an inverse. And luckily, it's really not too bad. If you think about this kind of thing where like f takes x to y, and then the inverse should take you back to where you start, then it's kind of reasonable to think of algebraically finding an inverse in just two kind of quick steps. The first step is literally just swap x and y. And that's kind of just because it is just because the inverse swaps the direction, right? We go y to x instead of x to y. And then, so let's just do this one at a time. So if I take this function here, if I swap x and y, I literally mean put x where y is, and then y where x is. So that would be the first step. And then we're just so used to functions that are written as y equals. So to get the inverse in a form that we're sort of used to, just turn this thing into a y equals function. So I would probably, to get rid of the cube root, I'm going to cube both sides. Then I'm going to minus 5. And that would be it. This would be the inverse function to this one up here, this cube root, right? Shouldn't be surprising that cube root and cubes are inverses in math. And just to show you that they really do work as inverses, right? If we do something like, f again composed with f inverse of x, we should go back to where we started x. And so I just want to show you that that's going to happen. So I'm going to take the cube root of something plus 5, which is my f, right? And the thing that I'm going to take it of is x cubed minus 5 in there. That's composing the function, sticking the inverse in to the original function. And then in here, I'll simplify this a little bit. I can do minus 5 plus 5 and get plus 0, right? And then cube root of x cubed is x. And so you can see you really did it. You started with x and you ended with x. You've created this loop, right? And you've gone back to where you start. So they really are inverses. That is typically how you're going to do this. There is a graphic way to do this, but it's not as useful, but I still want to show it to you just because I think it's important to see it. But this is how you're going to almost always find the inverse of a function. You're just going to do this swap x and y, solve for y kind of thing. So graphically, to swap x and y, because that was the first step algebraically, we are going to utilize a function y equals x. So all of these pictures here have the diagonal line y equals x drawn. And it's a little hard to see, but there's actually a dot right there. And what we're going to do is this line basically says y is x, x is y. It's the one that sort of swaps the two, right? So if we actually move over that line, we've in a sense swapped x and y just like our first step over here said to do, right? So basically, graphically, the way you do this is it's like an art problem. You just do a reflection across the line. So, here's my point that I want to find the inverse of. I need to go perpendicular to the y equals x line and just flip it over and go the same amount the other way. And you'd be right here, right? And you can really see that point, the green point, would be the inverse if you look at the numbers, right? So if I think about the numbers, I'm taking -2, and then the function sends that to 2, right? So that was the original function. Plug in -2, you get 2 out. That is a function. It's totally fine. And now we're taking 2, right? And we go plug that in, and we get -2 out. And that's the inverse, right? You can see it's created the loop, all by just literally doing like an art problem where you switch over the line y equals x. So that's how you do it. You literally just reflect over, okay? And what I would want you to try is, so you got 3 more here, and I just want you to try to think about what they would look like. So I'm going to give you a second, pause the video, think about how to get the inverses. All right, so I'm going to move on and we'll do this one next, I guess. So if I was doing the inverse of this, I would think about a few points in particular. So take that point. That is on the line of reflection, so there's no way that it's going to move, right? That one should stay put. Take this point up here. If I flip that over, it was on the y-axis, so it should flip to the x-axis. Kind of likewise, like this point over here, should flip over the line and end up right there, right? So if you kind of connect these things, right, you can kind of see that this green one is really what the inverse should look like. And you can kind of see, if you tilt your head and kind of line your head up with the y equals x line, you can see this is nice and symmetric with the line. Like it truly is how the reflection across that line would work, right? This one up here, I might do the same thing, do something like, this point's not going to move. This one, move over here, but then this point flips over here, right? So you can kind of see that this is basically what you get. This one's kind of weird because what is happening here is that the inverse function is actually equal to the original function. And that can totally happen in math. You can have an inverse which is equal to the original function. Actually, y equals x is an example of that. Y equals x is a function that is its own inverse. And that's it might sound weird, but that's literally an example right there. And there's other ones too. This is actually another example of it. And so that Weird, but can happen. This one's just kind of fun. So if I was flipping this over this line y equals x, right, I have, maybe I would take it point by point or something, take that eyeball. That I is kind of at, I think it's at -1, 3. So it's going to flip to 3, -1, right? This one over at -3, 3 would flip to 3, -3, right there, right? And you probably can already kind of see where this is going. Its mouth, this point is going to flip here. This one's going to flip here. So he's kind of like smiling like that. I might delete some of this because it's going to get hard to see. And then his head is just going to kind of fill in. And, this part that went below is why I'm going across the y-axis right there. So it really should dip over to the left of the y-axis too. But yeah, you can see the symmetry again, right? Like this and this are symmetric with the line y equals x. Now, certainly, this original function failed the vertical line test and the horizontal line test, so its inverse is not a function. But we can still think of what the graph would look like, as a function. This one, too, fails the vertical line test, so the inverse would fail the horizontal line test. Or you can think green is the original function, and this green one fails the horizontal line test, which is why the blue one here, which was our original one, would have failed the vertical line test, right? So the blue is not a well-defined inverse for green. That's like what the horizontal line test there is doing. These two are really nice. These two are both inverse functions. Have well-defined inverses. Or the original functions that have well-defined inverses. All right, so just want to do a few more kind of quick examples here. And actually, the first one we already kind of did. I sort of already said that one. So a function can be its own inverse. Yes. And we already saw the example y equals x. And there's honestly lots of other ones. What's another one that's kind of fun? So if you graph f of x equals, let's say, -1 over x, that is actually another function that is its own inverse. These are called rational functions. We've sort of seen these here and there in this course so far, but that's another one. This next question just says, if f of 2 is 5 and g of 3 is 5, then what is f inverse of g of 3? Okay, so the way I would just do this, g of 3, right? So if I do g of 3, right, g of 3, right by this, is 5. And if f inverse of 5, you would have to go here, right? So if you take f inverse of both sides, right, you cancel that f right there, and you'll have 2 would equal f inverse of 5, right? It's just going to reverse the thing around. So that's how you would kind of do that one, right? If 2 goes to 5 through f, then 5 goes to 2 through the inverse. This one asks basically is first sketch this thing out and its inverse, and then is the inverse a function? So kind of using the graphical method to find inverses. So, just quick recap with function transformations. That's a shift right 3. That's a vertical stretch by 2. That's a vertical flip. And then last but not least, that's a shift up 4. So if I graph what that would be, I get this. And so if we think about that thing, right, we can see that this thing is going to be just like quadratic. It'll fail the horizontal line test. And so its inverse would not be well-defined. I might actually go a little further because I'm going to sketch the inverse here. So we'll do, that's good. That's good too. better. Okay, there we go. To sketch the inverse from a picture, right? So we got the line y equals x here, right? And I'll do the inverse in like purple or something. You know, this point, not going to move because it's on the line of reflection. This one was at 1, 0, so it's going to move to 0, 1. You know, take this point. This was at 0, -1, so it's, or sorry, -2, so it's going to move to -2, 0. This vertex point was at 3, 4, so it's going to move to 4, 3, right? And so you can kind of start to, well, let's get another one over here. So this one is 5, 0, so it's going to move to 0, 5, right? So I think that's enough. So that is roughly what the inverse of the function would be. Now the inverse is not, you know, a function, right? Because we see that the original one failed the horizontal line test. So the this purple graph is going to fail the vertical line test, not going to be a well-defined inverse. And so all absolute value functions also fail the, they don't have well-defined inverses, is what I was going to say. All right, just one more quick problem. So you have function g here, and I give you a composition f composed with g of x. And the question is, what function would describe f given this g? So this one has actually nothing to do with inverses, but a lot of times what's tricky with inverses still boils down to composition. And so I wanted to get at that part of here a little bit. So it's kind of just like a puzzle, right? Like you have a square root function as the composition, and you know what you're popping into the f, but you have to figure out what f is, right? And basically it's just kind of guess and check, right? I would look at this 5 and this 4, right? You know, I'm plugging this into some sort of square root thing, and when I do it, I get a +4 instead of a +5, right? So it's probably not so bad to kind of just, you'll eventually get there. If you just think about it, you can get that there has to be like some sort of square root x minus 1 going on, right? So if you took this and you plugged it in there, then f of g of x would be, equal to the square root of x squared plus 5 minus 1. And then you would truly get x squared plus 4. So a lot of times composition is actually what is trickiest with inverse functions, and they are so closely related. Finding an inverse is really not that bad. You literally just go and you swap x and y, and then you solve for y. And you might want to do it in a picture sometimes, like I did kind of here, but it's really not the best way to do it. The best way is definitely like, again, what I did here. So that is kind of it for inverses. We're going to use this kind of stuff for another day, and then we're going to finally be able to move on to talking about root functions.